So with this, I would like to introduce our speaker for the first place, Leo, with the paper Cyberlog Towards Accurate Long-Term Visual Localization. Unfortunately, the speaker cannot be here today, but we will play back the pre-recorded talk.
Hi, I'm Liu, a researcher from the Cyberverse department, Huawei. I'm talking about Cyberlog Towards Accurate and Long-Term Visual Localization. This is a joint work with my colleagues Ni Yukai, Yang Xiao, Xu Qichao, Jia Miao,
There is
Ren
some
Yangdong,
significant
Xiang,
noise.
Luo
I think
and
it's
Ni
not coming
Jiangwei.
from our end.
Let's first look at the definition of this localization problem. For a scene, organizers provide multiple pre-recorded images with accurate 6 degrees of freedom camera poses from GPS and IMU. Recording multiple image sequences for a scene would let the pre-recorded map be robust with respect to environmental changes. Given query image sequences, the task is to estimate 6 degrees of freedom camera poses in a world coordinate system. Let's see our overall solution. For each reference sequence, also known as session, we use 4 different methods to reconstruct 4 maps for robustness purposes. I will talk about the 4 methods later. Given query image sequences, for each query image, we estimate 1 global camera pose using the 4 maps, resulting in 1 global camera pose for 1 session. Since we have multiple sessions, for each query image, we can estimate multiple global camera poses, 1 for each session. For this figure, the PKIs in circles denote global camera poses. For each query image, the estimated multiple global camera poses are at a different level of accuracy. Some are even wrong. We thus propose a consensus set maximization module with integer programming solver to select the best camera pose for each query image, resulting in 1 global camera pose for each frame. For example, for frame 1, we select the first pose, and for frame K, we select the middle camera pose. Collecting these poses resulting in a global absolute pose track. Our last contribution is the pose refinement and polish module. It takes SLAM relative poses, 2D matches, and the best global absolute camera pose track, and global 2D 3D matches corresponding to this track as inputs, and estimate query poses. We use the outputs of this pose refinement and polish module for submission. There are 4 modules for our method. Robust 3D mapping to reconstruct 3D maps for a scene. Single frame localization to estimate a global absolute camera pose for a query, and consensus set maximization to select the best camera pose for localization with respect to multiple reference sequences. The final pose refinement module fuses global localization and local SLAM. Let's see the first module, robust 3D mapping. Before mapping, we do 3 image pre-processing. They are semantic segmentation, low-light image enhancement, and image resizing. The semantic segmentation is used to remove dynamic objects, since these dynamic objects are meaningless for reconstructing the same map. We have found that removing these dynamic objects would result in about 1 to 2% localization performance improvement on the validation set. Though removing dynamic objects has limited effectiveness for single-frame localization, it is very important for dynamic SLAM. The second one is low-light image enhancement. We perform this step for low-light images, and we will show this effectiveness later. The last is image resizing, as neural networks are sensitive to image size. After image preprocessing, we use 4 methods to reconstruct 4 maps for a reference sequence. The first one is structure from motion with superpoint, superglue, and ground truth poses. This process is performed on the provided keyframes only, and we use image retrieval to find potential matchable image pairs, extract superpoint features, and use superglue for matching features, followed by triangulation using ground truth poses. We note that the performance of superglue is the best for matching sparse features. However, it is time-consuming. In our latest work, we propose a FGC net. We have achieved 4 times speed up with competitive performance. Please refer to our paper for the 2 new modules. The second reconstruction method is SLAM with superpoint, nearest neighbor match, and ground truth poses. We use all frames, extract superpoint features, and perform nearest neighbor match for consecutive images. We note that the reconstructed map is even better than the first map, according to our validation results. The third reconstruction method is very similar to the first one. The only difference is that we use lofter with quad tree attention to match images. The last reconstruction method is estimating stereo disparity for each keyframe, resulting in a local 3D map for each keyframe. With pre-reconstructed maps, we perform single-frame localization. We follow the standard pipeline, image retrieval, image matching to find 2D, 3D matches, and then do perspective endpoints for absolute camera pose estimation. We have one contribution here, that is the image retrieval. We use our own network trained on the Huawei dataset, duped as subplace here. Please see the following table for the comparison with respect to state-of-the-art methods. It outperforms others on both standard benchmarks, left column, and on the challenging datasets, right columns. Please also note that for the lifetime Old Town dataset, after performing image enhancing, we get better results. For example, for the recall at 1, we got about 20% improvement. Since we have 4 maps, we can obtain 4 sets of 2D 3D matches for each map. We merge all the 2D 3D matches from 4 maps and then do PMP to obtain the final pose, 1 pose for each session, each reference sequence. We have multiple sessions. For each query, we have 1 global pose. And how to combine sessions? A simple baseline is merging 2D 3D points matches again and then do PMP. It has 3 weaknesses. The first, it is slow for ransack since we will have many 2D 3D matches. Second, it is risky. Most often, it will produce averaged or one dominant pose. And finally, it only works when results from sessions are compatible. We give a new method. Select the best pose with integer programming. Let's look at the left figure. We have 3 consecutive frames at time k, m, and n. For each timestamp, we have a number of global poses according to C sessions. We can build a densely collected graph for 2 consecutive frames. For clarity, we only draw edges collecting the pose PMJ here. The edges EKIJ are binary variables, either zeros or ones. 0 means the edge is not selected, and 1 means the edge is selected. The problem is defined as finding the optimal edge variables collecting nodes, poses. We formulate the problem as a consensus set maximization and solve it using integer programming. Here, the SKIJ means the number of inline 2D matches from SLAM, since for each edge we can first compute the corresponding relative pose and then count the number of inline 2D matches using the sampling metric. The optimization process has 2 constraints. The first one is the summation of edges for 2 consecutive frames equals to 1. This constraint is imposed to ensure the collectivity of the global pose track. The second constraint is used to ensure the coexistence of nodes and edges. We will give more details in our follow-up technical report. At this moment, please keep in mind that after this consensus set maximization step, we only have 1 global camera pose for each query image. The final module of our method is pose refinement. It combines the global localization with local SLAM to find the best query poses. Let's look at this figure from top to down. We first have a global 6 degree of freedom camera pose for each query and the corresponding 2D 3D matches corresponding to pose PK. Additionally, we have a latent weight WK describing the accuracy of the 2 global information. In the middle, we have latent 6 degree of freedom poses, which we aim to solve for queries. In the bottom, we have information from local SLAM. For 2 consecutive frames, we have relative pose Z and the corresponding 2D matches. Our objective is fuse the global localization and the SLAM to estimate latent variables. They are latent weights and latent 6 degree freedom pose. Our objective function is given by this equation, which aims to jointly solve pose x and weights w. The 4 loss terms are global pose error, 2D 3D reprojection error, relative pose error, and sampling error. We solve this equation alternatively minimizing weights and poses by expectation maximization, inspired by Professor Ginhim Lee's work. Please refer to our follow-up technical report for details. Finally, let's see some results. We use the challenging lifetime old town dataset and city loop dataset for demonstration. The first column corresponds to the translational error thresholds. For the old town dataset, we have 3 reference sequences. The recalls at different error thresholds are given. Our in-peak programming process can achieve better accuracy, and the best accuracy is obtained after final post-refinement. Same observations can be found on the city loop dataset. We also show camera trajectories for the old town and city loop dataset. Note the outlier poses for the old town dataset from the single frame localization step. And after consensus set maximization and post-refinement, we can obtain a very smooth post-trajectory, in line with the ground truth post-trajectory. To conclude, our method combines best practices of a single-frame localization and SLAM. For single-frame localization, we have contributions for both image retrieval and image matching. For combining the global localization and SLAM, we propose 2 new methods: a consensus maximization module to select the best post track, and the final refinement to fuse global localization and local SLAM. That's all. Thank you.
So we thank the speaker for the great talk. And are there any questions from the audience? I can start with a question. Leo, can you hear us?
Yeah, I can hear.
Okay, great. Thanks for your great talk. Your results are really astonishing, really amazing results. I would be interested in the pre-processing part of your method. You've been mentioning that removing dynamic objects leads an improvement of 1–2%. Can you elaborate a bit on, especially the nighttime series seems to be quite challenging, on how the image enhancement helps to improve the results?
Yeah, I think on the nighttime images, performing this low-light image enhancement would improve the brightness of the image, and we use one pre-trained network to enhance it to improve the brightness. And after performing this enhancement, we can extract better 2D feature points with more discriminative features. And I think that's the reason why we can get 1–2% localization improvement. Thank you.
Okay, thank you. I have another question regarding the computationally demanding of your method. How long will it take to run one localization candidate? Because it seems like quite computationally demanding if you basically relocalize against many reference frames.
Yeah. And this time, when we submit the result, we use one boundary adjustment to perform all the sequences. But we have also experimented one online version, and we found that it can be achieved in real time, but with lower accuracy. To submit, we use the final boundary adjustment, and it takes about 20 to 30 minutes to finish.
Okay, so basically, I assume this is kind of, is it implemented on a CPU or on a GPU, or can it still be accelerated?
CPU. We implement in CPU. Yeah, with CPP.
Okay, thanks a lot. Are there any additional questions from the audience? If not, we would like to thank the speaker again for the great talk, and we would move on in the session.